Welcome back to General Chemistry. Let's have a look at the relationship that Clausius and Clapeyron developed as an equation to see how we can get the enthalpy delta H of vaporization when we know what is the relationship between the vapor of the pressure of vaporization, the vapor pressure, and the temperature. Normally we have data that would look like this, where you have that at 200 degrees the pressure is 0.08 for this particular substance. At 220 Kelvin you have 4.5 torrs. Remember that we're using torr, which is the unit for pressure relative to the height of the mercury column in a barometer. 1 torr is equal to 1 millimeter of mercury and is named after Torricelli, a very important Italian scientist. The other thing we have to keep in mind is that the temperature for these relationships is always in Kelvin. So if we start with degrees Celsius, we have to change those into Kelvin. We already have the Kelvin here and we have the pressure here, so if we want to find what the delta H of vaporization is, we'll have to see what is the relationship between these two. It's not easy to see in a table, so one thing we can do is to plot these numbers and see what kind of relation do we find. So in this case, we are looking at the relationship here between the temperature and the pressure follows this kind of, let me get rid of that. It's kind of a exponential, try to make this a exponential shape there. So there is a relationship here, but we cannot see it very well. So what Clapeyron and Clausius did was to find a relationship where instead of having the pressure and the temperature, they were looking at the logarithm of the pressure to make this exponential curve align. So what they did was to plot the logarithm of the pressure versus 1 over temperature, and they found out that the equation that controls that relationship would look something like this, where the logarithm of the pressure of vaporization is going to be some kind of constant times 1 over T. This would be our x here plus some other constant. And they found that this constant here is minus the delta H of vaporization normalized by the universal gas constant R, where remember R will have a value something like 8.314 joules per mole Kelvin. And in this case, we can see that this would be something like a straight line, where this here would be the y, and the 1 over t would be the x, and this would be the slope and the ordinate to the origin here. So if we plot this 1 over t as an x and logarithm of t, we get a shape similar to this. And here you see that we have this kind of a straight line here going like this, right? Let me see, it would go something like this, right? Where the slope here is equal to the negative of the delta H of vaporization divided by R. So the thing is, what would be the value for this slope? So there are different ways of doing it. Of course, you can use your calculator. What I did is use the Excel spreadsheet, and as I look at the Excel spreadsheet, I can get a line that goes through those points here, and the Excel spreadsheet is giving me this slope here, which is negative 3733.5, and so I know now that the slope is equal to negative 3733.5, and this is going to be equal to the negative or the delta H of vaporization divided by R, right? So if we put the numbers for R here, multiply this number here, we get a delta H of vaporization. So if we do that, and of course have a look at this thing, we have that we have negative here and we have negative here, so those two negatives can cancel out. So what you finally get is that the delta H of vaporization is equal to 8.314 joules per mole Kelvin times 3773.5, and then this will be Kelvin, so you cancel out the Kelvin, you get delta here. If you do that, you will get a number that it should be something like 31,400. So I'm going to change the 31,000 to kilo, and this is going to be kilo joules per mole. So that's how you get the value for the delta H of vaporization when you know the relationship between temperature and the pressure of vaporization at different points. I hope you enjoyed this video.